Um, Thank you for joining our presentation on the YOLOv4 paper today. So our high-level agenda today is going to be a brief introduction to some of the metrics that are used and how YOLO works, followed by some of the improvements made in YOLOv4 and also the performance of YOLOv4. So before we get started, a brief introduction on object detection. So object detection is a computer vision task in which we locate the presence of an object with a bounding box and types or classes of the located objects in the image. Basically, the input is an image or a video, and the output is a bounding box defined by the coordinates of a class for each bounding box, as we see in the picture here. Object detection generally falls into either a machine learning based approach or a deep learning based approach. And you only look once, also referred to as YOLO, is a deep learning based approach for object detection. So before we proceed, let's familiarize ourselves with some of the metrics and how they are evaluated as they are used in object detection. The first metric is called intersection over union, also called IOU. So object detection systems make predictions in terms of a bounding box and a class label. So in practice, the bounding boxes predicted have the coordinates x1, x2, y1, y2. So most of the, sometimes these coordinates are sure to be off from the ground truth. So that it's not always an exact match of the coordinates. So we know that we should count a bounding box prediction as incorrect if the class altogether is wrong. But again, a question arises as to whether we should draw the line on the bounding box overlap. So basically, intersection over union provides a metrics to set this boundary at, measured as the amount of the predicted bounding box that overlaps with the ground truth of the bounding box divided by the total area of both bounding boxes. So picking the right single threshold for IOU is a bit arbitrary. So one research might say 60% overlap is sufficient, and another might come in and say we need 70% or 75%. So this is the reason why we need to have a single metric that considers all the thresholds. And this is where our next metric, which is called the mean average precision, comes into picture. So models that involve an element of confidence can trade off precision for recall by adjusting the level of confidence. So in other words, if a model is in a situation where avoiding a false positive is more important than avoiding a false negative, it can set its confidence threshold a bit higher in order to encourage the model to only produce high precision predictions. But again, this comes at the expense of lowering its recall. So this process of plotting a model's precision and recall as a function of model's confidence threshold is called a precision recall curve, as we see here. As the model gets less confident, the curve slopes downwards. So the average precision, or AP as it is also called, is calculated as the weighted mean of precisions achieved at each threshold. So in order to calculate, there's another metric called mean average precision, also called MAP. What we do is we draw a series of precision recall curves with varying IOU thresholds. So these are a couple of the main metrics that every or most object detection models need or use. Now going back to YOLO, or you only look once. So this is very popular because it achieves a really high accuracy while also being able to run in real time, and it's like really, really fast. The algorithm only looks once at an image in a sense that it requires only one forward propagation pass through the neural network's predictions. So I got this image of the version 1 documentation for YOLO. The document mentions that they used a 24 convolutional layers followed by 2 fully connected layers. But the image that I have here is a fast YOLO. So this uses fewer convolution layers. It just uses 9 instead of 24 and fewer filters. So other than this, all the training and testing parameters are all the same between YOLO and fast YOLO. But how does YOLO actually work? So we have other classification networks such as like regional proposal classification networks like fast RCNN and faster RCNN, which perform detection on various region proposals and thus end up performing multiple predictions for various regions within an image. Whereas the YOLO architecture, as seen previously, is a fully convolutional neural network, and it just has to look at the image once. So it basically converts an image that's of n by n dimensions. It passes it through the fully convolutional neural network, and the output is an m by m prediction. The network divides the input image into a grid. So we can define what the grid size and what each cell size is, and a predetermined number of bounding boxes. So these bounding boxes predict the x coordinate, y coordinate, the width, height of the object. And the boxes also include a confidence score of how sure the object belongs to a certain class. The confidence prediction represents the IOU between the predicted box and any ground truth box, which is usually hand labeled data. And ultimately, each grid cell ends up giving us a set number of bounding boxes with a confidence score and classification for each. Now, let's take an example. So let's say in our example, we have an image, and let's say we divide this image into a 3 by 3 grid, and the total number of classes we are working with is 3. So for each grid, the prediction will be an 8 by 8, will be an 8-dimensional vector. In this vector, the PC defines whether an object is present in the grid or not, and the Bx, By, Bh, Bw specify the bounding box of the object, and C1, C2, C3 represent the classes. So if the class C2 has been identified in the image, this would be set to 1, and C1 and C3 would be set to 0. So let's take a look at the top left where PC is 0. So in this particular grid, the object was not detected. So PC is 0, and we don't really care about the remaining values. Now, for a grid where an object is found, we can see the PC value is 1, and also the particular class this object has been predicted to, the value is 1. So the next step would be to figure out the bounding box for each of the objects. So the blue dot here in the image is the x and y coordinate of the midpoint of the object with respect to the grid. So in our example, it comes to about 0.4 and 0.3 for the x and y coordinates. And ph, which is the height, is a ratio of the height of the bounding box, the red box in the image on the right, to the height of the corresponding grid cell, which in our case comes to around 0.9 in this particular example. And BW, which is the width, is the ratio of the width of the bounding box to the width of the grid cell, so which comes to about 0.5 again, approximately. And the next step is to evaluate the intersection over union and something called a non-max suppression. So In order to decide whether the predicted bonding box is giving us a good outcome, we use intersectional union or IOU. And if the IOU value is over a certain threshold, then the prediction is good. Otherwise, we discount. So the threshold value again here is arbitrary and might have to be changed or tweaked a bit based on the problem we are trying to solve. And the other problem we usually run into is that the algorithm might detect an object multiple times with varying probabilities, as we see in the right here. So in order to clean up the multiple detection, YOLO uses something called as the non-max suppression. Basically, the way this works is for each detection, the highest probability is chosen for each detection. So in this case, the box with the probability of 0.9 would be selected first. Then the boxes which have the highest IOU with the current box are suppressed. So basically, for the object on the right here, we see three bonding boxes with probability 0.9, 0.6, and 0.7. What ends up happening is the boxes with probability 0.6 and 0.7 are suppressed, and in the end, we only see one single box with a single probability, which is the highest probability. And this same process is applied to all objects in the image. And the final result is that we have one image with bounding boxes for each of the objects and the class of the object. So the biggest advantage of YOLO over other approaches is that it's very fast and can run in real time. There have been multiple versions of YOLO, and each one has improvement in the speed and accuracy. And Gokul will be walking us through the improvements that have been implemented in before. Over to you, Gokul.
Thank you, Shiva. You can hear me, right?
Yeah.
Go and share my screen. Okay. So you have seen the groundwork of YOLO, and now let's go on with YOLOv4. So they make one strong claim here that this model is very powerful and it can run on a 1080 GPU. That is something that like, someone can afford, and it's like running the model on a laptop itself. So let's look at what makes it so powerful and what are the different strategies that were used over here. Just like any other object detection model, it has the same kind of model structure, the YOLOv4 model. So it has the input and then the backbone. It's used for extracting the features with the it goes on as the layer goes deep, it gets more complex features, and then these features, feature extractors, and are then fed into the neck to get the feature maps. And from the feature maps, they use it to get the dense predictions. That is actually using it to get the classification and regression of bounding boxes. So this is what the base architecture of YOLO or any object detection model for the case looks like. But let's look at what's so special about it, especially the bag of freebies and bag of specials. So I would say YOLOv4 is more of a, it's the result of a lot of study, because they have tried out a lot of approaches, including this. These were like the state of the art detection strategies that were used. So they have tried to optimize on the feature extraction part and the data augmentation part, etc., etc. So bag of freebies is mainly aimed at improving the training part of the model, especially with respect to extracting the right features and then improving the training cost. Whereas bag of specials is aimed at improving the accuracy of the model. That is where the inference cost comes into play. So they have tried out a lot of data augmentation methods. So these are the various things that they tried. So these are like simple augmentation with respect to images, like crop rotation stuff. So and then they tried out mix-up, where you try to combine two separate images, and you change the alpha value a little bit, so that like you can try to detect multiple objects in the image. And then they also tried out cut mix, where they cut a part of the image and then overlay it on top of another image and try to predict the detect the bounding boxes. And then they used a new data augmentation method named Mosaic, where they combined 4 images into one image. So this is mainly to optimize the batch normalization. In batch normalization, what you do is you normalize the um, the weights with respect to one particular layer and across many images. So here you are achieving an even more bigger batch normalization with having multiple images clubbed into one image. And blur is just another simple data augmentation method. So Shiva has already informed you about the IOU loss. Now they have used a different IOU here that's called coverage IOU. This is how it is different. The normal IOU takes into account the X, Y, W edge and the distance between the center points. But here they are also taking into account the coverage area and the aspect ratio. So if you had seen in previous, if you had run a previous YOLO model, you would have seen that the bounding boxes are not very fine grained, but here you can see that the bounding boxes are actually much fine grained, and it it captures only the particular image under consideration, particular object under consideration. And as part of the bag of freebies, they have also tried something called self-adversarial training. What they are trying to do is it's like a simple adversarial training strategy where you try to change the image, but then you try to alter the image. They would say that as perturbations. So you try to perturb the image, but still try to predict or detect what object is present in the image. So in the forward pass, they try to alter the image rather than the weights, and then they try to detect the objects on top of the altered image. And then they tried a couple of activation functions, and then two of the activation functions came out very successfully. So one was Mish and the other was Swish, that's mentioned here. So out of these two, Mish seemed to be performing very well, and it gave out a better accuracy. And this is the activation function for Mish activation. And then this came out very recently, and you can refer to this paper over here that's mentioned here. And so they tried out all these methods, and then they combined it with different activation functions. And you can see the top 1 and top 5 accuracy here. So with respect to Mish, they are getting 79.8 and 95.2, which is the highest. And so it's again the same with these three things. And so they are studying the influence of the bag of freebies and the Mish activation function on two separate models. So here they are using darknet 53, and here they are using resnext 50. So these two, resnext 50 and darknet 53, they are different backbones that they're using that is trained on top of huge data sets like ImageNet. And in the bag of specials, what it does is, like I told you, it improves accuracy, right? So it uses mechanisms like attention to improve the accuracy. We all know that attention is performing well in a lot of fields, and it's trying to improve the accuracy. So here's what spatial attention does. What it does is once you get the feature maps, so it runs the attention mechanism in a different space, that is across the channels. So across the channels, they run the attention mechanism with the convolution layer, and finally they use the sigmoid to create an attention mask, and finally they multiply the feature vector with the attention mask to get the spatial attention results. So let's look at the studies that were taken in YOLOv4 to achieve the best model. So here you can see that the spatial attention mechanisms gives the best accuracy rather than when compared to all other approaches. And also they have compared it with two different backbones that seem to be performing well, but there was only a slight difference. And so this is just the ResNext 50 backbone with the bag of features alone. And this is the same with the addition of Mish activation function. And this is the counterpart with respect to the darknet 53 model. And the darknet 53 model gave better accuracy with a AP score of 43. And also the main claim is that, so the first point, if you see in YOLOv4, they have told that they're able to achieve this accuracy with a single GPU model. So it's very curious how they did that. So the main thing is that they've improved the model drastically, and they've also claimed that the mini batch size does not affect the training of the model. So here, if you can see, without the mini batch, uh, and on top of the Resnex 50 with a mini batch size of 4, and without these features, the bag of freebies and bag of specials, by varying the mini batch sizes alone, they have the average precision score is actually drastically changing. But here, if you see, with the features of the freebies and the specials, even if you change the mini batch size from 4 to 8, the average precision doesn't change very much. So this is one big improvement that the model creators have done. And this is the final accuracy comparison. So as you can see, the y-axis specifies the average precision score, and the x-axis specifies the frames per second. Most object detection models try to compensate between them, but if they try to improve the frames per second, the accuracy falls very low. And if they try to improve the accuracy, the frames per second is very low. But YOLOv4 has come out really good, and it's standing in the top right of the curve, which means it gives better FPS as well as a better average precision score. So this is the average case that they're considering. These are probably the lower bound and upper bound, the worst case scenarios. They haven't explained this graph very much, but I believe this is the explanation that I can give. And this is the AP score and the AP50 score, the comparison of the both. So that's pretty much about YOLOv4. So the bag of freebies and bag of special and the different feature extraction methods is what makes YOLOv4 really great model. If you guys have any questions, Shiva and I would be happy to take it. And then thank you so much. This we don't have any questions. So,
I have a question. Hello?
Yeah, sure.
Yeah. So how does YOLOv4 compare against Data?
Sorry?
Data, the new Transformers object localization model? Was there
I
any
believe
comparison with that?
the paper doesn't provide any comparison with DETR, because DETR is rather the latest model. That and yeah, but I think in real time, YOLOv4 performs better. And as far as I know, I've run some tests on DETR, and I wouldn't say the results are very good. It's just an end-to-end transformer model. It's a huge leap for an object detection, where there they use backbone and all. Like in a normal object detection, we use backbone, neck, and then a head. Whereas in a DETR, it's an end-to-end transformer model. But as far as accuracy, if you consider the accuracy, I would say YOLOv4 is a better alternative right now.
All right, thank you. Yeah, I'll check it out.
Okay. Subhantra ma'am, should I stop the recording? On the call. Shiva, can you hear me?
Yeah.
Okay, so like
Okay.
we
Guess
can just
there
wrap
aren't
up, right?
any more questions. Thank you guys for joining our session today. Have a good evening.
Bye bye.
See ya.
Thank you. Thank you.